Okay, so we have seen in the last lecture the famous theorem of Montel on normality of families, and what it says is that if suppose you have a family of meromorphic functions defined on a domain, the domain can be in the extended complex plane. To decide that the family is normal, all you have to do is to ensure that all the functions in the family do not take 3 distinct values in the extended plane, okay. And because you are working with meromorphic functions, you have to allow the value infinity, because that is the value that a meromorphic function at a pole will take, okay. And but of course if you are looking at a family of analytic functions, okay, then the condition is much more simpler. You have to just find 2 complex values which the functions in the family do not take, and if that is true, then the family is normal, okay. This is the great theorem of Montel, and so you see it is the key to proving the Picard theorems, which we will do, right. So so here is Picard's big or great theorem. Okay. So you know what the theorem is. The theorem is that if you take a function which has an isolated essential singularity, then the image of any neighborhood of that singularity is either the whole complex plane, or it is the complex plane minus a single value, okay. That means it means that it can at most omit one complex value, alright. And what is the restatement? The restatement is that if it omits more than one value, if it omits 2 values, that is something that cannot be, that is not possible, okay. So what we will do is we will assume that it omits 2 values, and then use the Montel criterion that a resulting family of zoomed functions is normal, okay, and examine the limit of the zoomed functions, and that will give you the proof, okay. So so let me state it. Let f of z, let f be let f have an isolated, let f of z have an isolated at z is equal to z naught, then the image under f of any deleted neighborhood of z naught is either all of the complex plane or omits at most one value in C. So this is Picard's theorem, okay. And of course, because this is valid for every neighborhood, it means that it will take except for one value which it might omit, all other complex values it will take infinitely many times, because the same way if you find a point where it will take that value, then you can find a smaller neighborhood, you can take a smaller neighborhood, deleted neighborhood of z naught, and in that neighborhood also again it has to take that value, and you can go on like this. Therefore it will take every value except one value infinitely many times, okay. That's amazing behavior of a function, analytic function, around a isolated essential singularity, okay. So this is the theorem, and so what is the proof? The proof is by contradiction, using the zooming process, so the zooming process has been, we have been using it right from Zalcman's lemma, okay. And what is the main idea behind the zooming process? The idea behind the zooming process is, as you zoom into a normal point, then all the zoomed functions will converge normally to a constant function, and if you zoom to a non-normal point, then all the zoomed functions will converge to a non-constant meromorphic function, Okay, that is the basically the principle. All right. So so what we will do is, so assume f omits two values in f omits two values in C in some deleted neighborhood uh, 0 less than mod z minus z naught lesser than say rho. Okay. So you have to show that f either takes all values or it will take all values except one. So if you want to contradict that, you have to assume that f omits at least two values. Okay. So let us assume that. All right. So what you do is, so here is it. So here is my diagram. So I have so this is the complex plane. This is z plane, and I have this point z naught, and there is this small disk surrounding z naught, radius rho. This disk with radius rho, and on this disk f doesn't take two values, two complex values. That means there are two distinct complex values which f will never take. It may not take many more values also, but at least two values it misses. Okay. And what am I going to do? I am going to construct a sequence of zoomed functions. So what is the sequence of zoomed functions? What you do is, well, take any so before that let me write it ideologically. Zoom into the function f at z naught itself. Okay. Mind you, the function in the z naught is an isolated singular point. It's an essential singular point. Therefore, in the deleted neighborhood of z naught, in this deleted disk, this punctured disk, okay, centered at z naught radius rho, you throw out the point z naught. In the punctured disk, the function is analytic, mind you. Okay. And what I am going to do is I am actually going to zoom into z naught. Okay. I am going to just zoom into z naught. And how do I zoom into z naught? By taking smaller and smaller disks of smaller and smaller radii which are centered at z naught, and of course I have to exclude z naught because z naught is a pointer of singularity of f. Okay. So what you do is zoom in to z naught. Okay. And so let me say that is, take a sequence epsilon n tending to 0 plus 0 less than epsilon n lesser than rho. Okay. So you take a sequence of smaller and smaller radii, okay, and let Gn of zeta be the zooming of f, the same function f, centered at z naught. The scaling factor is 1 by epsilon n and the variable is zeta. Okay. So this means that you are just taking f of z naught plus epsilon n times zeta. This is the function. Okay. So this is what my Gn is. So I am using that single function, I am constructing a family of functions. Using the single function f, I am constructing a family of functions Gn. Okay. And where are these Gn's defined? So you see the so this is a z plane, and then if you look at it correspondingly, you have the so this is the complex plane which is a z plane. Then I also have the complex plane which is zeta plane. Okay. And in the zeta plane, what happens is that if I take this disk centered at the origin and radius, if I take the radius to be rho by epsilon n, okay, that is for mod zeta less than rho by epsilon n, mod epsilon n zeta will be less than rho, and therefore this is the so this is the disk in which Gn is defined, but the only thing is it's not defined at the origin, because at the origin corresponds to z naught, and for and f at z naught is not defined because z naught is a singularity of f. Okay. So so let's write that down. Gn is defined, so let me write this here. Gn of zeta is defined in 0 less than mod zeta less than rho by epsilon n. And of course, the point about this whole business is that since epsilon n tends to 0 plus, rho by epsilon n tends to infinity, and therefore g and zeta is going to be you can talk about convergence or normal convergence of g and zeta on the whole punctured plane, okay, except that there is a whole plane except the origin, because eventually any compact subset of the punctured plane other than which does not contain the origin is going to be contained in the domain of g and zeta for n sufficiently large, okay. So so let me write this down. Note that any compact subset of C not containing the origin is going to be in the domain of definition of g n zeta for n sufficiently large, okay. So now I want you to just watch. See, after all, the values of gn in this punctured disk centered at the origin radius rho by epsilon n correspond to exactly the values of f in the punctured disk centered at z naught. The values of f inside this whole disk, punctured disk centered at z naught radius rho, they are exactly the values of gn in the punctured disk centered at the origin radius rho by epsilon n, because this is just a scaling and a translation, okay. Now you see now f, but what have we assumed about f? We have assumed that f omits two complex values, okay. F is an analytic function and it omits at least two complex values in this disk, punctured disk centered at z naught radius rho. Therefore each of the gns will also omit those two values in their domains, okay. And of course each of the gns are also analytic functions, because they differ from f only by bilinear transformation consisting of a scaling and a translation, okay. So but now we are in good shape, because what we have done is we have been able to get a family of functions gn which are analytic, okay, and which omit two values. Now immediately Montel's great theorem will tell you that it has to be normal, and you will get a convergent subsequence, and then you have to examine the limit, okay, and the limit will give you a contradiction, alright. So basically the contradiction will be that the limit function at the origin will examining the limit function at the origin will tell you that the origin has to be either a pole or a removable singularity for f, which is not true. I mean, analysis of the limit function will tell you that you take this limit function will also be defined on the punctured plane, okay, because all the original gns are all defined outside 0, okay. So if you analyze the limit function, see, the limit function is like zooming into f at z naught infinitely many times, okay. So the behavior of the limit function at the origin, which is an isolated singularity, will reflect upon the behavior of f at z naught, and by analysis we will show that if you analyze the limit function, there are only two possibilities. Z naught should either be a removable singularity or it has to be a pole, and both of these are contradictions, because I assume z naught for f to be a essential singularity, okay, and that's how the proof goes. So it becomes as simple as that. So let me write this down. Note that Gn is a normal family, as it also does not assume the values that f omits, okay. So what does it mean? If it's a normal family, it means that and it's a normal family and mind you, for Gn, because these are zoomed functions whose domains are becoming bigger and bigger and bigger, okay, you can think of them as a normal family, you know, in with a limit in the punctured plane, all right. So what you must understand is that if you take for example, if you take the punctured unit disk, okay, if you take the punctured unit disk, then for n sufficiently large, all the GNs are going to be defined, their domains are going to become bigger and bigger, and they are going to contain the punctured unit disk, okay. So you can say that the if you want to take the, if you want to talk about the domain of the GNs, okay, you can assume that for n for n sufficiently large, the domain contains the unit disk if you want, or for that matter any finite disk, okay, with of course the origin omitted, okay. And when you take the limit function, that is because Gn is normal, if you take the limit function will be defined on the whole punctured plane, because it will make sense, because you are covering every point in the plane literally, because for every point in the plane, if you take epsilon n sufficiently small, rho by epsilon n becomes sufficiently large, and Gn's beyond a certain stage will be defined at that point, and therefore the limit of all the, if you take a convergent subsequence of Gn's, as the limit will also be defined at that point, okay. So let me write this, thus Gnk, thus there exists Gnk a subsequence that converges normally to G on to G of zeta, if you want, on C minus the origin, okay. So this happens because what is the meaning of normal family? Normal means that normally sequentially compact, that means give me any sequence, there is a normally convergent subsequence. So if when Gn itself is a normal family, it is already a sequence, so it will have a normally convergent subsequence. So you have a subsequence Gnk which converges normally to G on C minus 0, okay. But the point is that it's not what is important is that it is G lives in a neighborhood of 0, okay. And now try to understand, each Gn is analytic on the punctured disk, on a punctured disk centered at the origin, okay. Therefore this limit function G is a normal limit of analytic functions. We have already seen such a normal limit can have only two possibilities, either the normal limit can completely be analytic, or it can be identically infinity. These are the only two possibilities. So let us write that down. Thus G is identically infinity, or G is analytic in C minus 0, okay. Now let us look at both of these cases. Suppose G is identically infinity, okay. Suppose G is identically infinity. So what does it mean? What this will mean, see, think of it heuristically. G is f zoomed infinitely at z0, and if G is identically infinity, what you are actually saying is that f is infinity in a neighborhood of, f is going to infinity in a neighborhood of z0, right, because the values of G are just limits of values of Gn's, and the values of Gn's are just values of f in smaller and smaller neighborhoods. So if G is identically infinity, okay, that means that the Gn's are getting larger and larger in modulus, okay, and that means that the values of f are getting closer and closer to infinity as you approach z0, but that means z0 is a pole, but that is not possible because z0 is an essential singularity. So this is not possible, so you have ruled out this case, okay. So let me write this down. This means that G of zeta is infinity for all zeta in C minus infinity. I will have to make use of the fact that Gn converges to G normally, okay. G is not just the, it's not simply limit of Gns, of course it is pointwise limit of Gns, but it's not, it's more than that, it is not just a pointwise limit, it's a normal limit. So the convergence is uniform on compact subsets, okay. So you know Gn of zeta converges to G of zeta uniformly on mod zeta is equal to say R for any R greater than 0, because you see mod zeta equal to R is a circle in the zeta plane centered at the origin, radius R, and that is certainly a compact set, it is closed and bounded, and G is a normal limit, therefore the convergence Gn to G should be uniform on any compact subset, so it has to be uniform on mod zeta equal to R, okay. But of course what is G zeta? G zeta is infinity if G is identically infinity. So what this and what does uniform convergence mean? It means that you know all the Gns, they will come to within an epsilon of G zeta, okay, if you take n sufficiently large irrespective of zeta, right, that is what it means, okay. But of course you want to come to an epsilon of infinity, so you will have to be careful and you will have to use a spherical metric, okay. So let me write this down, thus given epsilon greater than 0, the spherical distance between Gn of zeta and G of zeta, which is actually infinity, can be made less than epsilon for n sufficiently large, and for all zeta with mod zeta equal to R, okay. But now but what is G and zeta? You see, but G and zeta, our definition is just f of z0 plus epsilon n zeta, this is what it is, okay. And as you know and you see, even if mod zeta is R, okay, if your epsilon n's are becoming smaller, so you are covering smaller and smaller disk, you are covering smaller and smaller circles centered at z0, okay, and therefore what you are saying is that the function values of f on smaller and smaller circles centered at z0 are getting close to infinity, okay, and that is enough to tell you that f, the limit of f as z tends to z0 is actually infinity, which means that z0 has to be a pole, but that is a contradiction to our assumption that z0 is actually an isolated essential singularity, okay. So let me write this down. This means that the spherical distance between f of z and infinity can be made less than epsilon uniformly on compact subsets of mod z minus z0 lesser than epsilon n for n sufficiently large. Okay. So you know, because what you must understand is that this this R is this capital R is at our disposal. You can make this capital R as small as you want, close to 0, you can make it as large as you want, okay. So you can literally cover all the circles centered at z0 of a fixed radius, okay, below a certain positive value. So in some sense therefore you are able to cover a complete deleted neighborhood of z0, okay, that is the whole point, alright. So so this implies z0 is a pole of f, which is a contradiction, because we have assumed Z0 to be an essential singularity. Okay, so thus you f the limit, the zoomed limit function g cannot be identically infinity. Okay, therefore what is the other possibility? It has to only be an analytic function in the punctured plane, punctured at the origin. Okay, thus g is analytic in the punctured plane. Okay, and what does that mean? It means that of course origin is a singularity. Origin is an isolated singularity for g. Okay, and now you can ask what kind of singularity it is, but the point is that again you should not try to study the singularity of g at the origin. You should not do that, because after all g at the origin is going to reflect f at Z0. Okay, so because mind you, the gns are all zoomings of f at Z0 and their limit is g. Okay, so g is some kind of infinite zooming of f at Z0. G at the origin is infinite zooming of f at Z0. Okay, therefore you should not study g at origin, but you must make use of the fact that g is analytic in the outside the origin. So if you again take this mod zeta equal to r, if you take a circle centered at the origin in the zeta plane, radius r, mind you again that's a compact set, and g being analytic, it's continuous, there on a compact set it will be bounded. Okay, now this bound will apply to f in a neighborhood of Z0. Okay, and we'll tell you that f is bounded in a neighborhood of Z0, but then Riemann's removable singularities will tell you that Z0 has to be a removable singularity, and again there's a contradiction, and that's the proof of the theorem. Okay, the proof of the theorem becomes so simple. Okay, so let's go to the other case. Again there exists an m greater than 0 such that again on mod zeta equal to r greater than 0, there exists an m greater than 0 such that mod g is less than or equal to m. Okay, and but after all since gn converges to g normally, in fact uniformly on mod zeta equal to r, because it's a compact set, we have f is bounded in a deleted neighborhood of Z0. This again implies by the Riemann's removable singularity theorem that Z0 is a removable singularity of f, again a contradiction. And that finishes the proof. There are only two choices for G, and both choices lead to contradictions. Okay, so so that's the proof of the famous big Picard theorem, and we can, as a corollary, we can deduce the little Picard theorem. What is the little Picard theorem? It tells you that the image of the complex plane under an entire function is again the whole plane or the plane minus a point. And now what is the proof? The proof is very simple. Take an entire function. Okay, of course you should take a non-constant entire function. Okay, because if you take a constant entire function, the image of a constant function is always only one point. So you must be careful. I must have been careful in saying that statement. If you take a non-constant entire function, then the image of the complex plane should be either the whole complex plane or complex plane minus a point. It can omit only one value at most. And what is the proof? Very simple. Take an entire function, okay, and look at the point at infinity. Okay, the point at infinity becomes a isolated singularity because the complex plane is a deleted neighborhood of infinity in the external complex plane. Okay, so your function f, your entire function f has infinity as an isolated singularity. Okay, now For an isolated singularity, what are the possibilities? It can be removable, it can be a pole, or it can be essential. If it is removable, it means that if infinity is a removable singularity, it means that f is bounded at infinity, and that means that by Liouville's theorem f has to be a constant. So if I take f to be a non-constant entire function, okay, infinity cannot be a removable singularity, alright. So it can only be a pole or an essential singularity. If infinity is a pole, then we have already seen that f has to be a polynomial, okay, and you know a polynomial will take all values because of the fundamental theorem of algebra. So if f has infinity as a pole, it is a polynomial, the image of the complex plane under f is the whole complex plane. You are using the fundamental theorem of algebra. So the only thing is infinity is an essential singularity. If infinity is an essential singularity for f, apply the great Picard theorem, okay. F can f has to, any neighborhood of infinity has to be mapped by f into the whole complex plane or the complex plane minus a point, but the complex plane itself is a deleted neighborhood of infinity. So f has to map the whole complex plane onto the whole complex plane or the complex plane minus a point, that is it, okay. So I will just write this down. So corollary, Picard's little theorem, if f is a non-constant entire function, then f of c is equal to c or c minus z0, okay, for some z0 in c. So proof is infinity is a singular point, is an isolated singular point for f in C union infinity, as C is a deleted neighborhood of infinity where f is analytic, okay. Thus infinity is either removable, pole, or essential. If infinity is removable, f is bounded at infinity, so by Liouville f is constant, a contradiction, because I am assuming f is a non-constant function, okay, a non-constant entire function. If infinity is a pole, we have seen earlier that f has to be a polynomial, be a non-constant polynomial. Which assumes all complex values by the fundamental theorem of algebra. Okay. So the only other case is when infinity is a pole. I mean, if infinity is an essential singularity, apply the big Picard theorem, or the great Picard theorem, f of c is c or c minus a point. Okay. So that finishes the proof of the little Picard theorem. And therefore you see you are able to prove the Picard theorems very easily. Okay. And the key to all this is this really great theorem of Montel, which is a criterion for normality of a family. Okay. And it's a very simple criterion in the sense that, you know, if you know a family of functions, if it's a family of meromorphic functions, if you know that it omits 3 values, okay, in the extended plane, then you know it's normal. If it's a family of analytic functions and it omits 2 complex values, then you know again it's normal. Okay. And the advantage of normality is that it is a kind of compactness, namely it's normal sequential compactness, which allows you to extract from any sequence a subsequence which converges normally, that is, which converges uniformly on compact subsets. Okay. So that finishes the proof of the Picard theorems, which were the main aim of this course. Okay. What I would like to next do is to tell you how powerful Zalcman's lemma is in several other contexts. Okay. Mind you that this reasonably simplified proof of the great Picard theorem was possible because of the Montel's theorem on normality. Okay. And that in turn was proved by using Zalcman's lemma. Okay. So these are all actually all the simplifications are because of Zalcman's lemma. That is the most important thing. Okay. So but this Zalcman's is, so similarly in the proofs of various other theorems and various other theories about complex functions, Zalcman's lemma provides us with easier proofs of some very deep results. Okay. And also provides us with new results, and I will try to outline those results in the coming lectures. Okay. So I will stop here.